In question 1, we are presented with a spinner that contains 12 sectors. 5 sectors are labelled with €6, 3 sectors are labelled with €9, and the rest are labelled with €0. In a game, a player spins the wheel and wins the amount of money that the arrow lands on. In part A, we're told that Fiona plays the game a number of times. We need to find the probability that she gets a €6, then a €9, then a €6 the first 3 times she plays. 5 out of the 12 regions are labelled with €6, so on an individual spin, the probability you get €6 is 5 over 12. 3 out of the 12 regions are labelled €9, so on an individual spin, the probability you get €9 would be 3 over 12. In this question, we need 3 things to happen. We need €6 on the first spin, €9 on the second spin, and €6 on the third spin. We can find the probabilities of each of these events individually. There's a 5 out of 12 chance to get €6 on the first spin, 3 out of 12 to get €9 on the second spin, and 5 out of 12 to get €6 on the third spin. In probability, the word "and" typically corresponds to multiplication. So here, we need to multiply together the 3 individual probabilities. This comes out as 25 over 576. When we write this as a decimal rounded to 4 decimal places, we get 0.0434. In part B, we're told that Rowan also plays the game a number of times. We need to find the probability that he gets €9 for the 3rd time on the 8th time that he plays. Well, there's 2 things that need to happen here. Rowan must win €9 exactly twice in the first 7 spins, and then win €9 on the 8th spin. On the previous page, we showed that there was a 3 out of 12 chance of winning €9 on any individual spin. So the probability of getting €9 on the 8th spin would be 3 over 12. The probability of getting €9 exactly twice in the first 7 spins is a bit harder. Here, we'll have to use the binomial distribution formula. N choose R times P to the R times Q to the N minus R. Here, N refers to the total number of trials. Since we have 7 spins, N is equal to 7. R is the amount of times we want our event to happen. Since we want €9 exactly twice, we will have R equal to 2. P is the probability that your event occurs on an individual trial. Here, there's a 3 over 12 chance we get €9 on an individual spin. So P is 3 over 12. Q is the probability that your event does not occur on an individual trial. We'll always have Q equal to 1 minus P. Here, Q is equal to 1 minus 3 over 12, which is 9 over 12. So, after subbing in, we get 7 choose 2 times 3 over 12 to the power of 2 times 9 over 12 to the power of 7 minus 2. When we type this into our calculator, we get 5103 over 16384. The word and corresponds to multiplication, so to get our final answer, we must multiply this by the 3 over 12 we obtained earlier. Rounded to 4 decimal places, this gives us an answer of 0.0779. In part C, we are told that Olga plays the game 2 times. We need to find the probability that Olga gets less than €16 in total. Well, when we think about the structure of the game, it's quite difficult to win at least €16 when you play the game twice. On each individual spin, you'll either earn €9, €6 or €0. The only way that you could end up with more than €16 is if you got €9 both times. A 9 and a 6 would give you €15, which isn't enough. So, the only way to get at least €16 is to get €9 on the first spin and €9 on the second spin. There's a 3 out of 12 chance to get €9 on an individual spin, so the probability here comes out as 3 over 12 times 3 over 12, which is 1 over 16. This is the probability of getting €16 or more in your first 2 spins. To find the probability that we get less than €16, we simply have to subtract this number from 1. This gives us 1 minus 1 over 16, which is 15 over 16. Written as a decimal with 4 decimal places, this comes out as 0.9375. In question 2a, we must prove that sine a plus b is equal to sine a cos b plus cos a sine b. In our proof, there's 3 results that we're going to need to use. Firstly, cos of 90 minus theta is equal to sine of theta. Second, sine of 90 minus theta is equal to cos of theta. And third, cos of x minus y is equal to cos of x times cos of y plus sine of x times sine of y. The starting point of our proof is to take statement 3 and let x equal to 90 minus a and let y equal to b. Now, I'll rephrase things a bit on the left-hand side. Minus a minus b can be rewritten as minus a plus b all in brackets. From here, we can use results 1 and 2 several times. Letting theta be equal to a plus b in statement 1, we see that cosine of 90 minus a plus b is equal to sine of a plus b. Letting theta be equal to a in statement 1, we see that cosine of 90 minus a is equal to sine of a. Letting theta be equal to a in statement 2, we get sine of 90 minus a being equal to cosine of a. Putting everything together, we've ended up with the sine of a plus b equal to sine of a times cos of b plus cos of a times sine of b. This is the exact statement we needed to obtain. In part B, we must use the formula from A and without using a calculator, find the value of sine 75 degrees. Well, since we can't use our calculator, we'll have to rely on the formula book. If you turn to the appropriate page, you'll find the sine, cos and tan values for 0, 90, 180, 270, 30, 45 and 60 degrees. The target angle, 75 degrees, can be written as a sum of two of these. 75 is equal to 30 plus 45. Hence, we can rewrite the sine of 75 as sine of 30 plus 45. The formula in part A said that sine of A plus B is equal to sine A cos B plus cos A sine B. Applying this statement with A equal to 30 and B equal to 45, we end up with sine 30 times cos of 45 plus cos of 30 times sine of 45. The values of each of these are given to us in the formula book. Sine of 30 is equal to a half. Cosine of 45 is 1 over root 2. Cosine of 30 is root 3 over 2. And sine of 45 is 1 over root 2. To multiply fractions, you multiply together the numerators and multiply together the denominators. We can use this to simplify. For 1 over 2 times 1 over root 2, the numerator will be 1 times 1, which is 1. The denominator will be 2 times root 2, which is 2 root 2. Now for the root 3 over 2 times 1 over root 2. The numerator will be root 3 times 1, which is root 3. The denominator will be 2 times root 2, which is 2 root 2. You'll notice that both our fractions have the same denominator. To add fractions with the same denominator, all you have to do is add the numerators. So the final answer here comes out as 1 plus root 3 all over 2 root 2. In part C, we must find all the solutions of the equation sine of t is equal to sine of 2t. Here, t is an angle between 0 degrees and 360 degrees. To start, I'm going to group everything together on one side of the equation. To remove the plus sine 2t on the right, we can subtract sine of 2t from both sides. Next, I'll turn to a result in the formula book which says that sine of 2a is equal to 2 sine of a cos of a. Applying this with t in the slot of the a tells us that sine of 2t is equal to 2 sine of t cos of t. Now we have a common factor of sine t on the left-hand side. This can be factored out. When we take out sine t from sine t, we're left with 1. When we take out sine t from minus 2 sine t cos t, we're left with minus 2 cos t. We've reached a situation where we have two quantities, sine t and 1 minus 2 cos of t, being multiplied together to give 0. The only way that this can happen is if one of the quantities itself is 0. So either sine t is equal to 0, or 1 minus 2 cos of t is equal to 0. We'll need to find the solutions for each of these equations. Focusing on the first of these, I'll begin by taking sine inverse of both sides. Using our calculator, sine inverse of 0 is 0. This tells us that the reference angle is t is equal to 0. Unfortunately, this isn't the only solution here. There's going to be a second solution contained within the first rotation of a circle. To find it, we can use our rules for the unit circle. If you have an equation involving sine, you should subtract the reference angle from 180. Here, the reference angle is 0, so the second solution will be 180 minus 0, which is 180. Another important thing to note here is that the interval we're given for t, 0 is less than or equal to t, is less than or equal to 360, contains both the endpoints, 0 and 360. Given any solution to a trigonometric equation, if we add a full circle of 360 degrees, you'll get another solution. We found that t equal to 0 degrees is a solution, so 0 plus 360, which is 360, is also a solution. This will have to be included because 360 degrees is contained within the given interval. Now, let's turn our attention to the second equation. 1 minus 2 cos of t is equal to 0. To begin, I'll remove the minus 2 cos of t from the left by adding 2 cos t to both sides. Next, I'll remove the multiplication by 2 by dividing both sides by 2. Then, I'll get rid of the cos by taking cos inverse of both sides. We can use our calculator to find cos inverse of 1 over 2. This will come out as 60 degrees. So the reference angle here is t is equal to 60. Again, we'll have to use our unit circle knowledge to find a second angle. Whenever you have an equation involving cos, the second angle is obtained by subtracting the reference angle from 360. Here, the reference angle is 60, so we get 360 minus 60, which is 300. Putting everything together, we ended up with 5 solutions. T equals 0 degrees, 60 degrees, 180 degrees, 300 degrees, and 360 degrees. In question 3a, we're given the coordinates of 3 points and asked to find the area of the triangle with these vertices. There's a result in the formula book which says that the area of a triangle is a half times the absolute value of x1, y2 minus x2, y1. However, there's an important caveat here. To use this formula, we must translate the points so that one of them becomes the origin, 0, 0. Here, I'll perform a transformation to our first point, 4, 6, so that it gets mapped to 0, 0. We begin with an x-coordinate of 4, and we want an x-coordinate of 0. So the shift here is minus 4. We start with a y-coordinate of 6, and we want a y-coordinate of 0, so the shift here is minus 6. So the overall translation is minus 4 to the x-coordinate and minus 6 to the y-coordinate. This translation should also be applied to our other 2 points, minus 3, minus 1, and 0, 11. Minus 3 minus 4 is minus 7, and minus 1 minus 6 is also minus 7. So minus 3 minus 1 gets translated to minus 7 minus 7. This gives us the x1 and y1 value for our formula. 0 minus 4 is minus 4, and 11 minus 6 is 5. So 0, 11 gets translated to minus 4, 5. This gives us the x2 and y2 values for the formula. Now, let's sub in our values. x1 is minus 7, y2 is 5, x2 is minus 4, and y1 is minus 7. When we perform the calculation inside the absolute value, it comes out as minus 63. To find the absolute value of a number, we turn it into its positive version. So the absolute value of minus 63 is plus 63. A half times 63 is 31.5, so the final answer for the area of the triangle is 31.5 square units. In part B, we're presented with 2 points, A and B. We must show that the midpoint of the line segment AB is a specified value. Well, the formula book contains a result about the midpoint. It's equal to x1 plus x2 over 2, comma, y1 plus y2 over 2. Our first point is A, which is equal to minus 1, comma, k. We'll label the minus 1 as x1 and the k as y1. Our second point is B, which is equal to 5, comma, L. We label the 5 as x2 and the L as y2. Let's sub these values into the midpoint formula. The x-coordinate can be simplified here. Minus 1 plus 5 is 4, and when we divide this by 2, we get 2. So we found that the midpoint is 2, comma, k plus L over 2. These are precisely the coordinates we needed to obtain. In B part 2, we are given the equation of the perpendicular bisector of AB. We need to use this to find the value of L and the value of K. The first thing to observe here is that the midpoint of the line segment AB will lie on the perpendicular bisector. This is because the perpendicular bisector goes exactly halfway between A and B. In the previous part of the question, we found that the midpoint had an x value of 2 and a y value of k plus L over 2. Since the midpoint lies on the perpendicular bisector, it must satisfy the equation of this line. 3x plus 2y minus 14 is equal to 0. 3 times 2 is 6, and the multiplication by 2 cancels the division by 2. 6 minus 14 is minus 8. And if we add 8 to both sides, we end up with k plus L is equal to 8. I'll label this equation 1. The strategy here will be to obtain a second equation in k and L, and then use simultaneous equations to solve for these variables. To obtain our second equation, it's useful to think about slopes. There's a fact that says the slope of the line ax plus by plus c is equal to 0 is minus a over b. The perpendicular bisector has an equation of 3x plus 2y minus 14 is equal to 0. So here we have a 3 in the slot of the A and a 2 in the slot of the B. It follows that the slope of the perpendicular bisector is minus 3 over 2. By definition, the perpendicular bisector of AB is perpendicular to AB. It follows that the slope of AB is plus 2 over 3. This comes from the fact that a perpendicular slope can be obtained if we flip the fraction and change the sign. Here, the sign changes from minus to plus, and the fraction flips from 3 over 2 to 2 over 3. So, we found that the slope of AB is 2 over 3. However, this slope can also be thought of from another perspective. There's a formula which says the slope of a line is equal to y2 minus y1 over x2 minus x1. We can apply this formula to find the slope of AB. A is equal to minus 1 comma k. We label these with x1, y1. B is 5 comma L, and we label these with x2, y2. Subbing these values in gives us L minus k over 5 minus minus 1. Since two minuses simplify to a plus, the denominator ends up as 5 plus 1, which is 6. This means that the slope of AB is equal to L minus k over 6. Earlier, we found that the slope of AB is equal to 2 over 3. So whatever L and k are, it must be the case that L minus k over 6 comes out as 2 over 3. This equation can be simplified a bit by multiplying both sides by 6. 6 times 2 over 3 is 4, so we end up with L minus k is equal to 4. I'll label this as equation 2. So, we found two equations in k and L. K plus L is equal to 8, and L minus k is equal to 4. We can use simultaneous equations to solve for k and L. The first equation has a plus k, and the second equation has a minus k. This means that if we add together the two equations, the k terms will cancel. When we add the equations, the k and the minus k cancel. L plus L is equal to 2L, and 8 plus 4 is equal to 12. So we end up with 2L is equal to 12. Dividing both sides by 2, we obtain L is equal to 12 over 2, which is 6. To find k, we should sub this value back into one of our equations. If we sub L equal to 6 into equation 1, we get k plus 6 is equal to 8. If we subtract 6 from both sides, we get k is equal to 8 minus 6, which is 2. So the final answer here is L is equal to 6 and k is equal to 2. In question 4a, we're told that the circle C has equation x minus h all squared plus y plus 3 all squared is equal to 12. In part I, we must write down the centre and radius of the circle. There is a result from the formula book which will help us out here. If we let h, k be the centre of the circle and r be the radius, then the equation of the circle will be x minus h all squared plus y minus k all squared is equal to r squared. Matching this formula with the equation we were given, we have a h in the slot of the h. We have a plus 3 in the slot of the minus k. And we have a 12 in the slot of the r squared. This gives us three equations. H is equal to h, minus k is equal to plus 3, and r squared is equal to 12. Changing the signs of both sides, minus k equal to plus 3 implies that k is equal to minus 3. Square rooting both sides, r squared equal to 12 implies r is equal to the root of 12. This means that the centre, h, k, comes out as h, minus 3. And the radius, r, is equal to root 12. In part 2, we're told that the perpendicular distance of a given line to the centre of the circle C is 5 units. We need to use this to work out two possible values of h. This question involves a perpendicular distance. The first step will be to open up our formula book and look this up. There's a result that says the perpendicular distance from the point x1, y1 to the line ax plus by plus c equal to 0 is the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. We are told that the perpendicular distance is 5 units, so we should set this expression equal to 5. The line that we are given can be written as 1x minus 4y plus 7 is equal to 0. The point that we have is the centre of the circle. In the previous part of the question, we found that this was h, minus 3. In the formula, a refers to the number in front of the x. So here, a is 1. B is the number in front of the y, so here b is minus 4. C is the constant term, so c is equal to 7. x1 and y1 refer to the coordinates of the point, so here x1 is h and y1 is minus 3. Let's sub these values into our formula. From here we can simplify. 1 times h is h. Minus 4 times minus 3 is plus 12, and then when you add on the 7, you get plus 19. 1 squared is 1, and minus 4 squared is 16, so underneath the square root, we get 1 plus 16, which is 70. We can get rid of the fraction on the left if we multiply both sides by root 17. This tells us that the absolute value of h plus 19 is equal to 5 times the root of 17. The absolute value of the positive and negative versions of a number both come out to the same thing. So there's two options for the expression inside the absolute value. Either h plus 19 is equal to plus 5 root 17, or h plus 19 is equal to minus 5 root 17. Focusing on the first case, subtracting 19 from both sides gives us h is equal to plus 5 root 17 minus 19. In the second case, subtracting 19 from both sides gives us h is equal to minus 5 root 17 minus 19. So there's the two solutions for h. In part B, we have a diagram of a circle S. We're given 3 points which are on the circle: A3, A minus 5, and 8, 1. We're also told that the radius of the circle is equal to root 20 units. We must use this information to find the equation of the circle. A very useful fact here is the following. If you draw a vertical line through a circle, the y value of the centre will be halfway between the y values of the two intersection points. Two of the points that we were given, a, 3 and a, minus 5, share an x value. This means that if we drew a vertical line at x equal to a, it would intersect the circle at these 2 points. Using our fact, we can deduce that the y value of the centre of the circle will be halfway between the y values of these 2 points. In other words, it will be halfway between 3 and minus 5. We can find this halfway point by adding together the numbers and dividing by 2. This gives us 3 plus minus 5 all over 2, which comes out as minus 1. We've shown that the centre of the circle has a y value of minus 1. This means that the coordinates of the centre are in the form h, minus 1 for some unknown value of h. The radius, r, was given to us directly. R is equal to root 20. We were asked to find the equation of the circle. It'll be a good idea to sub these values into the equation of a circle formula. X minus h all squared plus y minus k all squared is equal to r squared. H is still unknown, so we leave it as it is. K is equal to minus 1, and r is equal to root 20. Minus 1 is plus 1, and root 20 squared is 20. So we end up with x minus h all squared plus y plus 1 all squared is equal to 20. We've made good progress here, but we're not quite done. We still need to find the value of h. To do this, we'll use the fact that 8, 1 is on the circle. Any point on a circle must satisfy its equation, so this means we can sub in x equal to 8 and y equal to 1 into the equation of our circle. From here, we can do some algebra to solve for h. 1 plus 1 is 2, and when you square 2, you get 4. The plus 4 on the left can be removed if we subtract 4 from both sides. 20 minus 4 is 16. The square on the left can be removed if we square root both sides. We have to be careful and write in a plus minus sign here. This is because the positive and negative versions of a number both square to give you the same answer. The root of 16 is 4. to deal with the plus-minus sign, we should split into two cases. In the first case, we replace it with a plus, and in the second case, we replace it with a minus. Let's focus on the first case. 8 minus h is equal to plus 4. Here, I'll subtract 8 from both sides. Observe that 4 minus 8 is minus 4, and then change the signs of both sides. This gives us h is equal to 4. In the second case, we have 8 minus h is equal to minus 4. Here, I'll subtract 8 from both sides. Simplify minus 4 minus 8 to minus 12. And then change the signs of both sides. This gives us h is equal to 12. We've gotten two solutions for h, but only one of them makes sense in the context of the question. If you look back at the diagram, you'll notice that the centre of the circle must be to the left of the point 8, 1. This means that h, the x-coordinate of the centre, must be less than 8. This rules out the h equal to 12, so we conclude that we must have h equal to 4. To get our final answer, we should write this in to the expression we had for the equation of the circle. This gives us x minus 4 all squared plus y plus 1 all squared is equal to 20. In question 5, we're told that Rowan has a large number of cubes. Some are red, some are green, and the rest are blue. Rowan performs the following experiment. He picks 5 cubes at random, he records the colours of the cubes, and then he replaces them. He repeats this process 7 times. In the table that we're given, the 7 trials are labelled with the letters from A to G. Looking at the column of an individual trial tells us how many cubes of each colour there were. For example, in trial D, there were 2 red cubes, 3 green cubes, and 0 blue cubes. In part I, we must work out the mean and standard deviation of the number of red cubes. Well, looking across the 7 trials, the number of red cubes were 0, 3, 2, 2, 4, 5, and 1. We'll need to find the mean and standard deviation of this data. Thankfully, modern-day calculators can find these quantities for us. If you go to statistics mode and type in our data, then the calculator will return the mean and standard deviation for you. Rounded to 1 decimal place, the mean will come out as 2.4, and the standard deviation will come out as 1.6. If you want more details on how to do this calculator work, check out the video linked in the description. In part 2, we must work out the correlation coefficient between the number of red cubes and the number of green cubes. Again, this will boil down to calculator work. This time, there'll be 2 lists of data we'll need to input. For the x data, we should put in the values for the number of red cubes. 0, 3, 2, 2, 4, 5, 1. For the y data, we should input the values for the number of green cubes. 4, 2, 0, 3, 0, 0, 2. Once you've performed the necessary steps, your calculator will return the correlation coefficient for you. Rounded to 3 decimal places, it comes out as minus 0.762. In part 3, we're told that Rowan repeats the experiment a large number of times. We must explain why we would expect the correlation coefficient between the number of red cubes and the number of green cubes to be negative. Well, the core idea behind a negative correlation is that when one quantity goes up, the other quantity will go down. In this experiment, Rowan picks exactly 5 cubes on each trial. This means that the red cubes plus the green cubes plus the blue cubes must be equal to 5. If there's a large number of red cubes, then there won't be much space left over for the other 2 colours. This means we'd expect a small number of green cubes. As an illustration, if the number of red cubes was 5, then there's nothing left over for the green cubes and blue cubes. So if red cubes equals 5, then it must be the case that green cubes is equal to 0. Since larger numbers of red cubes correspond to smaller numbers of green cubes, we have a negative correlation between the 2 quantities. In part B, we're presented with a cuboid that is made up of a large quantity of small cubes. The width of the cuboid is 5 units, the height is 4 units, and the depth is 3 units. We are asked to consider the number of faces each small cube has exposed on the outside. As an example, the cube in the top right corner has 1, 2, 3 faces on the outside. The task here is to count up how many small cubes have 3 faces on the outside, how many have 2 faces on the outside, how many have 1 face on the outside, and how many have no faces on the outside. One of these values is filled in for us already. We're told that there's 22 small cubes with 1 face on the outside. So, if we're trying to look at the cubes with 3 faces on the outside, you'll notice that this only happens at a corner piece. I've coloured these in purple in the diagram. There's 4 corner squares on the top layer, and there'll be another 4 corner squares on the bottom layer. It's worth pointing out that one of these corners is hidden from view in the diagram. 4 plus 4 is 8, so we end up with 8 small cubes with 3 faces on the outside. The cubes with 2 faces on the outside correspond to the non-corner pieces which appear along one of the edges of the cuboid. I've coloured these in orange. If we focus on the top layer of the cube, we have 1, 2, 3, 4, 5, 6, 7, 8 orange cubes. By symmetry, there'll be 8 orange cubes on the bottom layer. Focusing on the 2 middle layers, you'll notice we have orange cubes stacked in towers of 2. 3 of these towers are visible. 1, 2, and 3. There'll be a 4th tower hidden behind view below this back left corner. Each of these towers contains 2 orange cubes, and we have 4 of them, so this gives us 4 times 2, which is 8 orange cubes across the 2 middle layers. 8 plus 8 plus 8 is 24, so we end up with a total of 24 cubes with 2 faces on the outside. The only thing left is to find the number of small cubes with no faces on the outside. Well, the dimensions of the cuboid are 5 units, 3 units, and 4 units. The total number of cubes will be 5 times 3 times 4, which is 60. We've already found the number of cubes with 3 faces, 2 faces, and 1 face on the outside of the cube. The number of cubes with no faces will simply be the leftovers that are needed to make up a total of 60. We can find the leftovers which are needed by subtracting each of the other numbers from 60. So we get 60 minus 8 minus 24 minus 22. This comes out as 6. In question 6a, we're given a statement and we must determine whether it's true or false. The statement is, 2 angles are vertically opposite if and only if they are equal in size. The phrase if and only if means that the implications must go in both directions. For this statement to be true, it would have to be the case that 2 angles being vertically opposite implies that they are equal in size, but also if 2 angles are equal in size, it implies that they're vertically opposite. If we think a bit about this second implication, we run into some issues. It is not the case that angles being equal implies that they're vertically opposite. To illustrate this, I've drawn a little diagram. The angles A and B here are alternate angles, which means they are equal. However, they are not vertically opposite. So we've shown that it's possible to have 2 angles equal in size, which are not vertically opposite. This means that the statement is false. In part B, we're presented with 2 diagrams of a rectangle, ACEG. In diagram A, various sides and angles have been labelled for us. We're told that GA has a length of 90 centimetres, AB has a length of 20 centimetres, and BC has a length of 30 centimetres. We've also been told that 3 of the angles in this diagram are equal. They've all been labelled with theta. In diagram B, the lines GE and BD are extended to meet at a point H. These 2 diagrams will be helpful for the questions on the next page. In B part I, we must prove that the length of FE is equal to the length of EH. And we're told to use congruent triangles in our proof. In diagram A, the angle DBC was labelled with theta. Since the lines GH and AC are parallel, we can use alternate angles to deduce that EHD is equal to theta. We're told that ACEG is a rectangle. This means that the angles in each of the corners must be 90 degrees. In particular, the angle FED will be 90. We know that FH is a straight line. Since angles on a line must add to 180 degrees, we know that the angle FED plus the angle HED must sum to 180. It follows that HED will be 180 minus the angle FED. We already found that this was 90, so we end up with 180 minus 90, which is 90 degrees. Now that we've filled in some of our angles, we're ready to compare the triangles EFD and EHD. the angle EFD is equal to the angle EHD because they've both been labelled with theta. The angle FED is equal to the angle HED since they're both 90 degrees. Since the three angles in a triangle always add up to 180 degrees, once you know two angles are equal, it must be the case that the third angle is equal. It follows that the angle FDE is equal to the angle HDE. The triangles also share a common side, ED. Since we've shown that the angles on each end of this side are equal, it follows that the triangles are congruent by ASA, angle side angle. In congruent triangles, the side lengths are equal. Since FE and EH are both opposite the green angle, it follows that the length of FE and the length of EH are equal. In part 2, we must find the size of the angle theta. To help us here, I've copied out the measurements from diagram A. We were told that GA was 90 centimetres, AB was 20 centimetres, and BC was 30 centimetres. This information can be used to fill in some other side lengths. The first thing to observe is that AFHB is a parallelogram. We know that AB is 20 centimetres and opposite sides in a parallelogram are equal, so it follows that FH is 20 centimetres. In the previous part of the question, we showed that FE and EH were equal in length. This means that the 20 centimetres for FH is split into two equal parts, 10 centimetres for FE and 10 centimetres for EH. Focusing on the original rectangle, the bottom side, AC, has a length of 20 plus 30, which is 50 centimetres. It follows that the top side, GE, must also be 50 centimetres. Since FE is 10 centimetres long, there's 40 centimetres left over for GF. Now, if we draw our attention to the theta in the right angle triangle AGF, you'll notice that the side opposite theta is GA, which is 90 centimetres. The side adjacent to theta is GF, which is 40 centimetres. In a right angle triangle, the tan of an angle is equal to the opposite over the adjacent. So we know that tan of theta must come out as 90 over 40. To find theta, we just need to get rid of the tan. We can do this by taking tan inverse of both sides. When we calculate tan inverse of 90 over 40, we get 66.0375. Rounding this to the nearest degree gives us our final answer that theta is equal to 66 degrees. In question 7a, we're presented with a diagram of a sloped road, AB. In this diagram, AC is horizontal and BC is vertical. We're told that AB is 70 metres and that BC is 9 metres. We are presented with a definition for the gradient of the road. It's defined to be the length of BC over the length of AC, written as a percentage. We need to find the gradient of the road correct to the nearest percentage. To use a definition of the gradient, we need to know two things: the length of BC and the length of AC. BC has been given to us directly. It's 9 meters. AC is not given to us, but we can find it using Pythagoras' theorem. This states that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The hypotenuse is the side opposite the right angle. Here, that's the 70 meters. This gets labelled with C in the theorem. The other two sides get labelled with A and B. Here, I'll label the length of AC as A and label the 9 as B. Subbing these into our theorem, we get 70 squared is equal to the length of AC squared plus 9 squared. 70 squared is 4,900 and 9 squared is 81. To get rid of the plus 81 on the right, we can subtract 81 from both sides. When we perform the calculation on the left, it comes out as 4819. Now, to get rid of the square, we can square root both sides. This tells us that the length of AC is equal to the root of 4819. We now know everything we need to calculate the gradient. By definition, the gradient is the length of BC over the length of AC. The length of BC is 9, and the length of AC is the root of 4819. Typing this fraction into our calculator gives us 0.12964747. We were asked to present the gradient as a percentage. To convert from decimal to percentage, we multiply by 100 and write in a percentage sign. When we round this off to the nearest percent, we come to the final answer that the gradient is 13%. In part B, Olga is looking at a point at the top of a hill, H. Olga wants to find the vertical height of this point. There's 2 points on the ground, R and P, which are 20 meters apart. And we know that the angle of elevation from R to H is 17 degrees. We're also told that the angle ORP is 88 degrees and the angle RPO is 87 degrees. We must use this information to find the distance from O to H. There's 2 triangles in our picture, ROH, which I've coloured in blue, and RPO, which I've coloured in red. The side that we're trying to find, OH, appears in the blue triangle. Unfortunately, we don't know much about this triangle. All we have is 2 angles, and we don't know any of the side lengths. In contrast, we know a bit more in the red triangle. Here, we have 2 angles and 1 side. An important thing to observe here is that the triangles share the side RO. If we can use the red triangle to find the length of this side, it will give us new information about the blue triangle and hence help us on our way to the final goal. The first thing to observe is that we know 2 out of the 3 angles in the red triangle. Since the angles in a triangle must add to 180, The third angle will be 180 minus 88 minus 87, which is 5. From here, we can find the length of the line RO by using the sine rule. A over sine A is equal to B over sine B. Here, I'll label the 5 degrees as capital A. The side opposite this, the 20 meters, will be labelled as lowercase a. I'll label the 87 degrees as capital B, and the side opposite this, RO, will be little b. Let's sub these into our formula. To find the length of RO, we'll want to get rid of the division of sine 87. To do this, we multiply both sides by sine 87. When we perform the calculation on the left-hand side, we find that the length of RO is 229.16 meters. Now, let's turn our attention to the 17-degree angle in the blue right-angle triangle. The side we're trying to find, OH, is opposite this 17-degree angle. The side adjacent to the 17 degrees is the 229.16 we've just found. In a right-angle triangle, the tan of an angle is equal to the opposite over the adjacent. Here, the angle is 17 degrees, the opposite is OH, and the adjacent is 229.16. To find the length of OH, we'll want to get rid of the division by 229.16. We can do this by multiplying both sides by this number. From here, we can perform the calculation on the left-hand side and round to the nearest metre. This brings us to our final answer. The length of OH is 70 metres. In the next part of the question, we're told that Olga has done some tests to measure her lung capacity. When she is resting, we can model the volume of air, V, in her lungs after t seconds with the following function. V of t is equal to 2 minus 0.4 times the cosine of pi over 2t. Here, the volume is in litres, and t is the time in seconds. An important thing to note here is that the expression inside the cosine is measured in radians. This means that we'll need our calculator in radians mode for the duration of this question. Along with this written description, we've been provided with a visual representation of the same information in the form of a graph. Here, the vertical axis represents the volume of air in litres, whereas the horizontal axis is representing the time in seconds. In part C, we must find the minimum and maximum values of our function. These have been labelled A and B in the graph. If we analyse the structure of our function, we'll notice that the 2 and the minus 0.4 are constants. They won't change depending on the value of t. The only thing that changes is the cosine pi over 2 times t term. This means that the minimum and maximum values of our function will occur at the minimum and maximum of this expression. A useful piece of background knowledge here is the following. The function f of x equal to cosine of x has a minimum value of -1 and a maximum value of +1. It turns out that cosine of pi over 2t will also have a minimum of -1 and a maximum of +1. Even though the expression inside the cosine is different, this only affects the speed at which the curve moves, not the minimum and maximum points. To find the minimum and maximum values of our function v of t, all we have to do is sub in the minimum and maximum values of the cosine pi over 2t. In other words, we should replace this expression with -1 and with +1. When we put in -1, we get 2 minus 0.4 times -1. This comes out as 2.4. When we put in +1, v is equal to 2 minus 0.4 times +1. This comes out as 1.6. So the answer here is that the minimum value for our volume, A, is equal to 1.6, and the maximum value of the volume, B, is equal to 2.4. In part D, we're asked to think about the connection between v dashed of t, the derivative of v, and whether Olga is breathing in or breathing out. The most important thing to remember here is that at its core, a derivative represents a rate of change. Here, the derivative v dashed of t represents the rate of change of our volume, v of t. Well, when Olga is breathing in, the volume of air in her lungs will be increasing. If something is increasing, this corresponds to a positive rate of change. So here, the rate of change, v dashed of t, will be positive. On the flip side, when Olga is breathing out, the volume of air in Olga's lungs will be decreasing. When something is decreasing, this corresponds to a negative rate of change. So here, the rate of change, v dashed of t, will be negative. In part E, we must use the formula for v of t to perform some calculations. Here, each answer should be rounded to 3 decimal places. First, we must find the volume of air in Olga's lungs half a second after t equals 0. Well, half a second after t equal to 0 corresponds to t equal to a half. We want the volume of air at this time, and that's precisely what our function v of t tells us. It tells us the volume. So here, all we have to do is substitute in t equal to a half into our formula. This gives us 2 minus 0.4 times the cosine of pi over 2 times a half. Ensuring that our calculator is in radians mode, we can perform this calculation and obtain the answer 1.717157. Since we were asked to round to 3 decimal places, the final answer here is 1.717 litres. In part 2, we're asked to find the rate at which the volume of air in Olga's lungs is increasing half a second after t equal to 0. An important thing to pick up on here is that this question involves a rate of change. We're not looking at the volume itself, but rather the rate at which the volume is increasing. As we mentioned earlier, the derivative v dashed of t will represent the rate of change. Solving this question will first require us to calculate this derivative. We'll do this by differentiating our function v of t is equal to 2 minus 0.4 times the cosine of pi over 2t. Since additive constants differentiate to 0, the 2 will differentiate to 0 and simply disappear. Differentiating the minus 0.4 cosine pi over 2t is a bit more tricky. The first thing to observe is that the minus 0.4 is a multiplicative constant. This doesn't disappear, but it won't interfere either. It simply hangs on the side of our expression when we differentiate. So the main work here will be differentiating the cosine of pi over 2t. Since this is a layered expression, we'll need to use our chain rule when we differentiate. In the chain rule, we need to perform two differentiations, an inner differentiation and an outer differentiation. In this expression, the inner layer is pi over 2 times t. A constant times t just differentiates to the constant. So pi over 2t will differentiate to pi over 2. Now, looking at the outer layer, our expression is in the form of cosine of something. If we look at our formula book, we'll see that cosine differentiates to minus sine. Here, the something that we had inside the brackets was pi over 2t. So this comes out as minus sine of pi over 2t. Now that we've performed our two differentiations, we get our answer for the chain rule by multiplying together these two expressions. This means that the cosine pi over 2t will differentiate to pi over 2 times minus sine of pi over 2t. We've done the hard work now since we found our derivative v dashed of t. We can simplify our expression slightly by observing that the two minus signs will multiply together to give a plus, and also observing that 0.4 divided by 2 gives us 0.2. This brings us to the result that the rate of change at any time t, v dashed of t, will be equal to 0.2 times pi times sine of pi over 2t. We want to know the rate of change half a second after t equal to 0. In other words, we need the rate of change when t is equal to a half. To find this, all we have to do is sub in a half to our derivative. This gives us 0.2 pi times sine of pi over 2 times a half. Again, ensuring that our calculator is in radians mode, we can perform this computation to get an answer of 0.444288. Rounding to 3 decimal places brings us to our final answer of 0.444 litres per second. In part F, we're told that Olga's breathing was also measured when she was doing gentle exercise. During this time, she has 3.6 litres of air in her lungs when she breathes in fully, and 1.3 litres when she breathes out fully. We're also told that she breathes in and out twice as many times per minute as when she is resting. We need to use this information to find a formula for E of t the volume of air in Olga's lungs during this exercise. The first thing to notice here is that the structure of E of t is very similar to the V of t we've been working with throughout this question. Because of this, we can use the structure of V of t as a starting point and then adapt things as necessary to get E of t. On the left here, I've copied out a portion of our graph for V of t, which was on the previous page. Earlier, we found that the minimum value of V of t was 1.6 and the maximum value was 2.4. In the diagram, I've also drawn in a horizontal line at the midpoint between the minimum and maximum. This takes place at the value of 2. You might notice that the additive constant at the beginning of V of t is also equal to 2. This is not a coincidence. Due to the symmetry of cosine, this number will always be equal to the midpoint between the maximum and minimum values. Labelling our graph for E of t in a similar way will allow us to find the value of A. Well, when exercising, we're told that Olga has 3.6 litres of air in her lungs when she breathes in fully. In other words, the maximum value of E of t will be 3.6. We're also told that there's 1.3 litres in her lungs when she breathes out fully. This means the minimum value will be 1.3. To find the label for our blue line, we simply need to find the midpoint of these two values. We do this by adding the numbers together and then dividing by 2. Here, we get 3.6 plus 1.3, all divided by 2, which comes out as 2.45. This will be our value for A. Turning our attention to B, if we look at V of t, we have a minus 0.4 in this slot. So, what does this correspond to? Well, in our graph, 0.4 is the distance between the midpoint to one of the extremes. In other words, the distance from 2 to 1.6 is 0.4, and also the distance from 2 to 2.4 is 0.4. Turning back to E of t, we can find the value of B by finding the distance between the maximum and the midpoint line. To do this, we take the maximum value, 3.6, and subtract the value for the midpoint, 2.45. This gives us an answer of 1.15. We do have to be careful with our signs here. In V of t, we found our distance to be 0.4, but in the formula it appeared as minus 0.4. For E of t, we found our distance as 1.15, but in the formula it's going to appear as minus 1.15. The minus sign here comes from the fact that our function is starting at its minimum value instead of the maximum. This is a result of the fact that our measurements are beginning at a time when Olga has breathed out fully. We're nearly there now. All we have to do is find the value of c. This represents the speed at which our curve is going up and down. When Olga was resting, we had a pi over 2 appearing in this position. We're told that when she exercises, she breathes in and out twice as many times per minute as when she is resting. One way to think of this is that our curve will move twice as fast. Since the pi over 2 was essentially representing the speed of the curve, if we want it to move twice as fast, all we have to do is multiply this figure by 2. This tells us that c will be equal to pi over 2 multiplied by 2, which comes out as pi. Putting everything together, our final answer is that e of t is equal to 2.45 minus 1.15 times the cosine of pi t. Question 8 involves probability and statistics. We're told that an online word game involves trying to guess a 5-letter word in as few attempts as possible. In the game, each player is given a score based on how many attempts it takes them to guess the word. Part A says that in Ireland, players' scores are approximately normally distributed, with a mean of 3.87 and a standard deviation of 0.36. A player is selected at random from the players in Ireland, and we must find the probability that this player has a score which is less than 3.5. The first thing to notice here is that we're working with a normal distribution. Our formula book contains probability tables full of information on this distribution, and this will be the key to solving this question. However, before we can use these tables, we must standardize our data. We do this by calculating the z-score. The formula is that z is equal to x minus mu all over sigma. Here, x refers to the target value, and in our question, the target is 3.5. Mu is the mean, and in our question, that's 3.87. Sigma is the standard deviation, and here that's 0.36. Subbing in these values and computing the answer gives us minus 1.027778. The tables in our formula book are formatted to receive numbers which have exactly 2 numbers after the decimal place, so we should round this number to 2 decimal places. This brings us to minus 1.03. Using this standardization, we can conclude that the probability our player has a score which is less than 3.5 is equal to the probability that a standard normal distribution is less than minus 1.03. We can visualize this as the area under the bell curve to the left of minus 1.03. In an ideal world, we'd be able to open up our formula book, look up this value, minus 1.03, and get our final answer from there. Unfortunately, the formula book only contains data for positive values of z. This means that we'll have to rephrase our problem so we end up with a positive value. Well, by the symmetry of the normal distribution, the probability that you're less than minus 1.03 will be equal to the probability that you're greater than plus 1.03. Since the total probability must add up to 100%, or 1 in decimal form, the probability that you're greater than 1.03 will be equal to 1 minus the probability that you're less than 1.03. Thankfully, we can find this probability by looking up page 36 of our formula book. The first 2 digits, 1.0, tell us which row in our table we should go to. The third digit, 3, tells us the column. When we look at the entry in this row and column, we see that the value is 0.8485. This tells us the area of the red region. But remember, we wanted the purple region, which was 1 minus the red region. So the final answer here will be 1 minus 0.8485, which comes out as 0.1515. In part B, we're told that a random sample of 64 Galway players has a mean score of 3.74. Based on this, a local newspaper claims that Galway players have a different mean score to the players in Ireland. In part I, we must use this information to construct a 95% confidence interval for the mean score of all Galway players. We should use the standard deviation of 0.36 in our calculations. We are working with a normal distribution here, and we're asked to find a 95% confidence interval. Thankfully, there's a direct formula that we can use to find this interval. It's the interval x bar plus or minus 1.96 times sigma over root n. Unfortunately, this result doesn't appear in the formula book, so it's something you'll want to have memorised before your exam. Here, x bar represents the sample mean, and we were told this was 3.74. Sigma is the standard deviation, and we're told to use a standard deviation of 0.36. Finally, n represents the sample size, and we have a sample of 64 players. Let's sub these values in. We can use our calculator to simplify the right-hand portion of this expression. It all comes out to 0.0882. Next, we'll need to deal with this plus-minus sign. This means that we should split into two cases, one with a plus and one with a minus. In the context of confidence intervals, the lower bound is obtained by using the minus, and the upper bound is obtained by using the plus. To finish off, all we have to do is to compute these two quantities. The lower bound comes out as 3.6518, and the upper bound comes out as 3.8282. In part BII, we must carry out a hypothesis test at a 5% level of significance to test the newspaper's claim. There's 4 things that we're prompted to do. State the null hypothesis, the alternative hypothesis, state our conclusion, and also justify the reason for our conclusion. Well, the newspaper's claim is that Galway players have a different mean score to players in Ireland. So we're interested in comparing the score of Galway players versus the overall average of all Irish players. When we do hypothesis testing, the null hypothesis tends to include equality. In other words, it's often in the form something is equal to something else. In this context, our null hypothesis is that the mean score of Galway players is equal to the mean score of Irish players. To find the alternative hypothesis, we need to consider what happens if the null hypothesis is not true. Here, the null is stating that two things are equal, so the alternative will simply be the statement that these two things are not equal. In other words, the alternative hypothesis is that the mean score of Galway players is not equal to the mean score of Irish players. To make our conclusion, we'll need to rely on the relationship between hypothesis testing and confidence intervals. In the previous part of the question, we found a 95% confidence interval for the mean score of Galway players. It was 3.6518 to 3.8282. One way to think of this is that we're assigning 95% confidence that the true mean is within these bounds. Well, if we're assigning 95% confidence to be inside the interval, then the remaining 5% will be for being outside the interval. The null hypothesis states that the mean score of Galway players is equal to the mean score of Irish players. If this were to be true, we would expect, with a 95% confidence, that the mean score for Irish players would be inside this 95% confidence interval. Well, in part A, we were told that the mean score for Irish players is 3.87. This value does not lie inside the confidence interval, and this can be viewed as evidence that the null hypothesis is not true. So the conclusion here is that there is sufficient evidence to reject the null hypothesis and conclude that the mean score of Galway players is not equal to the mean score of Irish players. In part C, we're told that a national newspaper conducts a survey on a random sample of N teenagers in Ireland. 35% of them said they play the online word game every day. Based on this, a 95% confidence interval was created for the percentage P of all teenagers in Ireland who play the game every day. Correct to one decimal place, the interval was from 26.5% to 43.5%. We must use this information to work out the value of N, the number of teenagers surveyed. The key to solving this question is the following result. For a 95% confidence interval, the margin of error for a percentage is given by E is equal to 1.96 times the square root of P hat times 1 minus P hat all over N. Here, E represents the margin of error, P hat represents the sample proportion, and N represents the sample size. If we can figure out what E and P hat are, then we can do some algebra and solve for N. Well, P hat is the sample proportion, and we're told that 35% of the sample play the game every day. So here, P hat is 35%, which as a decimal is 0.35. The margin of error, E, is the distance between an end point of the confidence interval to the centre point. Whenever we construct a confidence interval, we always do it around the sample proportion or sample mean. So the centre point of the interval here will be the 35% we found as P hat. We can compute the margin of error by finding the distance between the upper bound, 43.5%, and the centre point, 35%. This gives us 8.5%, which as a decimal is 0.085. Alternatively, we could have found the distance from 26.5% to 35%, and we would have got the same answer. Now that we found the values of p hat and e, let's put them into our formula. We want to solve for n here. In other words, we'll want to isolate the n all by itself on one side of the equation. A good place to start would be to strip away some of the layers of this expression on the right-hand side. The 1.96 represents multiplication, so this can be removed by dividing both sides by 1.96. Next, we can target the square root. The inverse of a square root is a square, so to get rid of this, we can square both sides. Looking at the right-hand side, the n is underneath the line in a fraction. This is a bit awkward. We can get it out of here by multiplying both sides by n. Now, we're pretty close to having n all by itself. The only issue is that it's being multiplied by an expression. To get rid of that, we should divide both sides by that expression. If we do some calculator work to compute the right-hand side, we end up with n is equal to 120.9639. N represents the number of teenagers, and this must be a whole number. So to get our final answer, we round to the nearest whole number. N is equal to 121. Part D says that a player wins the game if they guess the word with 6 guesses or less. The organisers of the game have recorded the following statistics for players in Europe. 80% of players win the game each day. 90% of players who win the game will play it again the following day. And 25% of players who do not win the game will play it again the following day. We must use this information to fill out the provided tree diagram. We're given a written description of the tree diagram, but I'll skip over it here because most of it is visually clear from the diagram itself. In our diagram, we're told that 360,000 people played the game on the 1st of June. Each of these players either won or lost the game, and this is the first split in our diagram. We are told that 80% of players win the game each day, which as a decimal is 0.8. That's why we have a probability of 0.8 leading to the win box. Well, if 80% of the players win, then the remaining 20% of players will lose. As a decimal, that's 0.2. So we can write the probability 0.2 on the branch to the lose box. To find the number of people who won and lost, all we have to do is multiply our total population of 360,000 by these probabilities. So, for the win box, we'll have 360,000 times 0.8. This gives us 288,000. For the lose box, we'll have 360,000 times 0.2. This gives us 72,000. Now we can think about the 2nd of June. We know that 90% of players who win the game will play it again the following day. As a decimal, that's 0.9, and that's why we have a 0.9 coming out from the win box. 25% of players who do not win the game, or lose the game, will play it again the following day. That's why we have this 0.25 coming out from the lose box. To fill in these two play boxes, all we have to do is multiply the previous number by the given probabilities. 288,000 times 0.9 comes out as 259,200. 72,000 times 0.25 comes out as 18,000. From here, we just need to repeat the process we've just done twice more. Once in the upper half of the tree, and once in the lower half of the tree. Starting with the upper half, of the 259,200 people who played on the 2nd of June, 80% or 0.8 will win, and 20% or 0.2 will lose. We can multiply by these probabilities to get the number of players who win and lose. Remember, 90% of players who win will play again the following day. So if we have a box labelled win, we should multiply by 0.9 to find the number of those players who play the following day. 25% of players who lose the game will play again the next day. So if we have a box labelled lose, we should multiply by 0.25 to find the number of those players who will play again the next day. Filling out the remaining entries in the lower half of the tree works in a very similar way. Of the 18,000 players who play on the 2nd of June, 80% or 0.8 will win. Multiplying these numbers tells us that we have 14,400 winners. 90% of players who win the game will play again the next day, so to find the number of these people who play again on the 3rd of June, all we have to do is multiply by 0.9. This gives us 12,960. Backtracking a second, of the 18,000 players on the 2nd of June, 20% or 0.2 will lose. Multiplying 18,000 by 0.2 gives us 3,600. 25% of players who lose will play again the next day, so to find the number of these people who play again on the 3rd of June, all we have to do is multiply by 0.25. This gives us 900. In the final part of the question, we're told that one person is picked at random from those who played the game on all 3 days. We must find the probability that this person lost on the 1st of June, 2nd of June, or on both. The first step here will be to figure out how many people actually played the game on all 3 days, 1st, 2nd, and 3rd of June. Well, we're in luck here. The way the tree diagram is structured is to track the number of players who make it through all 3 days. So to find the number of people who played on all 3 days, we simply need to see the amount of people who made it to the end. In other words, we should add up the values in each of the final 4 play boxes. When we do this, we end up with 213,444. So, how many of these people lost a game on the 1st of June, 2nd of June, or both? Well, the 186,624 in the top box represents the players who won on the 1st of June and 1 again on the 2nd of June. So these guys didn't lose on either day. The 12,960 in the second box represent the players who won on the 1st of June, but lost on the 2nd of June. So these guys did lose on one of the days. The 12,960 in the third box is for the people who lost on the 1st of June and won on the 2nd of June. So again, this represents players who did lose on one of the days. Finally, the 900 people in the last box lost on the 1st of June and lost again on the 2nd of June. So these guys also lost on one of the days. To find the total number of people who lost on the 1st of June, 2nd of June, or both, we must add together the numbers from these three boxes. 12,960 plus 12,960 plus 900. This gives us 26,820. To find the probability of picking such a person, we must divide this number by the total number of people who played on the 3 days. This gives us 26820 divided by 213444. If we simplify this fraction, it comes out as 745 over 5,929. Or as a decimal, we can write it as 0.125654. In question 9, Ava is looking at different ways to tile a region with shapes. We're considering two options: tiling with squares and tiling with regular hexagons. We're told that a square tile and a hexagonal tile each have an area of 140 centimeters squared. The first task is to work out the length of the side of the square tile, correct to 1 decimal place. Well, there's a well-known fact about squares which says that a square with a side length of L will have an area of L squared. We're told that the area is 140, so we can set L squared equal to 140. To solve for L, all we have to do is take the square root of both sides. We can use our calculator to compute the square root of 140. And when we round to 1 decimal place, we get our final answer that the length is 11.8 centimeters. In the next part of the question, we must find the side length of one of our hexagonal tiles. This is a bit trickier. Thankfully, we've been provided with a diagram with some helpful labels. In this diagram, the hexagon is split into 6 equal triangles. One of these triangles has 3 labels written in: a 60-degree angle and 2 sides marked as X. Since the hexagon contains 6 equal triangles, we can deduce that the area of the hexagon will be 6 times the area of one of these triangles. We know that the area of the hexagon is 140, so if we can write the area of a triangle in terms of X, we'll be able to use this equation to solve for X. To find the area of the triangle, we can use a result from page 16 of the formula book. It says that the area of a triangle is equal to 1/2 times A times B times sine C. Here, A and B refer to the lengths of 2 sides of the triangle, and C refers to the angle between these 2 sides. In the label diagram we've been given, we have two sides and the angle in between. To use our formula, we can let A be equal to x, B be equal to x, and C be equal to 60 degrees. Subbing these in gives us a half times x times sine 60. X by x simplifies to x squared, and using our calculator, sine 60 becomes root 3 over 2. To simplify further, we can multiply the half by the root 3 over 2, and this gives us root 3 over 4 times x squared. Now that we have an expression for the area of the triangle, we can write it into the equation we had and then solve for x. In our equation, the x squared is being multiplied by a constant, 6 times the square root of 3 over 4. To remove this multiplication, we should divide both sides by this number. We now know what x squared is equal to, so to solve for x, all we have to do is remove this square. We do this by taking the square root of both sides. We can use our calculator to compute the expression on the right-hand side. It comes out as 7.340710. We were told to round our answer to 1 decimal place, so the final answer here is that x is equal to 7.3 centimetres. In part B, Ava is considering a more complicated tile. Here, each tile consists of two parts. An arrowhead, A, B, E, D, which I've coloured in blue, and a quadrilateral, E, B, C, D, which I've coloured in red. In part I, we're provided with several side lengths. We're told that AD is equal to 8 centimetres, AE is equal to 6 centimetres, and ED is equal to 4 centimetres. In the diagram, one of the angles is labelled alpha, and we must show that alpha is equal to cosine inverse of 7 over 8. Well, if we take a look at the values we're given, they all live in the same triangle, AED. Let's focus in on this triangle. We know all three side lengths, and we're trying to find an angle. So all in all, we're working with 3 sides and 1 angle. This is precisely the setup we need to use the cosine rule. This says that a squared is equal to b squared plus c squared minus 2bc times the cosine of capital A. Here, capital A refers to an angle, and in our diagram that will be the alpha. Lowercase a is the side opposite this angle, and here A will be 4. B and C refer to the other 2 side lengths. Here we can let B be equal to 8 centimetres and C be equal to 6 centimetres. Let's sub these values into our formula. From here we can simplify a bit. 4 squared is equal to 16. 8 squared plus 6 squared comes out as 100. And minus 2 times 8 times 6 is equal to minus 96. The result we need to show has alpha all by itself on one side of the equation. So the target here will be to isolate the alpha. To start, we can get rid of the plus 100 by subtracting 100 from both sides. From here, we can simplify on the left. 16 minus 100 is minus 84. Next, we can get rid of the multiplication of minus 96 by dividing both sides by minus 96. Now, if we use our calculator to simplify the fraction on the left-hand side, it comes out as 7 over 8. Finally, to get rid of the cos, we need to take cos inverse of both sides. This tells us that alpha is equal to cos inverse of 7 over 8. This is precisely the result we needed to show. In part 2, we're told that the angles ADC and ABC are equal to 90 degrees. We must use this to work out the total area of the quadrilateral ABCD. A good place to start here is to focus in on the triangle ADC. This triangle makes up half of our quadrilateral, so if we can find the area of this triangle, we can simply double it to find the area of the quadrilateral. Well, we're told that the angle ADC is 90 degrees. In other words, it's a right angle. So we can use the results for sine, cos and tan in right angle triangles. We're trying to find the length of AC, and that corresponds to the hypotenuse in this triangle. Focusing on the known angle, alpha, the side AD, which is 8 centimeters, corresponds to the adjacent. Since we're working with the adjacent and the hypotenuse, we can use the result that cosine of alpha will be equal to the adjacent over the hypotenuse. In the previous part of the question, we found that alpha is equal to cosine inverse of 7 over 8. We've shown that the adjacent is 8 and that the hypotenuse is the side AC. Some nice cancellation happens on the left. The cosine will cancel the cosine inverse, so we're left with 7 over 8. Next, we can multiply both sides by the side length AC. And finally, we can divide both sides by 7 over 8. When we calculate 8 divided by 7 over 8 in our calculator, we get 64 over 7. Now that we know the length of AC, we have 2 side lengths and the angle in between. So we're ready to use our formula for the area of a triangle. A half times A times B times sine C. Here, we can let A be equal to the side length AC, which is 64 over 7. Set B equal to the side length AD, which is 8. And set C equal to the angle in between these sides, alpha. In the previous part of the question, we found that alpha is equal to cosine inverse of 7 over 8. Typing this big expression into our calculator will give us the area. It's 17.7051. We were asked to find the total area of the quadrilateral ABCD. But as we mentioned earlier, this shape is split evenly into 2 halves, an upper triangle, ADC, and a lower triangle, ABC. We've just found that the area of the upper triangle was 17.7051, and by symmetry, the area of the lower triangle will be the exact same. To find the total area of the quadrilateral, all we do is add the area of these 2 triangles. When we perform the calculation and round to 2 decimal places, we come to a final answer of 35.41 centimetres squared. In part C, Ava is looking at tilings of the unit circle. We are provided with a diagram of the unit circle, and there's been 3 points labelled: O, P and Q. We are told that the angle QOP is 45 degrees. To help visualise this, we should draw in the side QO. Something worth noting here is that QO is a radius of our circle. Since we're working with the unit circle, which has a radius of 1, we know that QO will have a length of 1. In the question, we are asked to show that the point Q has coordinates minus 1 over root 2, comma 1 over root 2. Well, the coordinates of a point correspond to the movements needed in the x and y axis to get from the origin to that point. We can visualise these movements if we drop a vertical line directly down from Q so that it meets the x-axis at a right angle. The horizontal x movement corresponds to this side length, and the vertical y movement corresponds to this side length. If we focus in on this right angle triangle, we can use some trigonometry to find these side lengths. Focusing on the 45-degree angle, the sides in a right angle triangle can be labelled with adjacent, opposite and hypotenuse. The hypotenuse is the side opposite the right angle, which here is 1. The opposite is across from the 45-degree angle, and here that's y. The adjacent is the third side, and here that's x. In a right angle triangle, the cosine of an angle is equal to the adjacent over the hypotenuse. Here, the angle is 45, the adjacent is x, and the hypotenuse is 1. If we type cosine of 45 into our calculator, we'll get 1 over root 2. The right-hand side, x divided by 1, simply simplifies to x. So we found that x is equal to 1 over root 2. We can find y in a similar way if we apply the result that the sine of an angle is equal to the opposite over the hypotenuse. In our triangle, the angle is 45, the opposite is y, and the hypotenuse is 1. If we calculate sine 45, we'll get 1 over root 2, and if we simplify the right-hand side, we can see that y over 1 is just equal to y. So we found that y is also equal to 1 over root 2. Now let's put everything together to get the coordinates of Q. We've shown that Q is located 1 over root 2 units to the left of 0. Since movement to the left corresponds to negative x values, we can conclude that its x-coordinate is minus 1 over root 2. We've also shown that Q is located 1 over root 2 units above 0. When we move upwards, it corresponds to a positive y value, so we can conclude that the y-coordinate is plus 1 over root 2. In the final part of the question, we're told that P lies on the x-axis. We're then told that the centre of our circle lies at the intersection point of two lines, the tangent line at the point P and the tangent line at the point Q. I've drawn in these tangent lines in our diagram. The tangent line at P is drawn in purple, and the tangent line at Q is drawn in pink. In the question, we've been asked to find the centre and the radius of the circle S. Well, we've been told that the centre occurs at the intersection point of the two tangent lines. The strategy here will be to find the equation of both tangent lines, and then use simultaneous equations to find the intersection point. To begin, let's focus on the tangent line at P. The first thing to think about is the coordinates of P. Since we're told P lies on the x-axis, it must have a y-coordinate of 0. Since P lies on the unit circle, which has a radius of 1, we can deduce that the x-coordinate is -1. To find the equation of the tangent line, we'll need to use a useful fact. The tangent line to a circle at a given point is perpendicular to the line joining that point to the centre of the circle. So, if we join our centre, O, to the point P, the tangent line will be perpendicular to this. Since the line OP is completely horizontal, a perpendicular line will be completely vertical. This means that the tangent line at P will be the vertical line which is drawn at an x value of -1. In other words, the tangent line will have the equation x is equal to -1. Now, let's turn our attention to the tangent line at Q. To find the equation of a line, there's two things we need to know: a point on the line and the slope of the line. We already know a point on this line, it's Q. And in the previous part of the question, we found the coordinates of Q. However, we don't know the slope. To find this, we can use the fact that I've written. The tangent line at Q will be perpendicular to the line which joins Q to the centre, O. The strategy here will be to first find the slope of this blue line, OQ, and then use this to find the slope of the pink line. Well, given 2 points on a line, we can find the slope of the line using the formula y2 minus y1 over x2 minus x1. As it turns out, we know the coordinates of 2 points on the line OQ, namely O and Q. O is the centre of the circle, which has coordinates 0, 0, and we label these with x1, y1. Q has coordinates -1 over root 2, 1 over root 2, and we label these as x2, y2. These coordinates were provided to us in the previous part of the question. If we sub these values into our slope formula and perform the resulting calculation, we end up with -1. So the slope of the blue line, OQ, is -1. The pink line is perpendicular to this, and there's a trick we can use to find a perpendicular slope. We flip the fraction and change the sign. To do this, it would be wise to first express our slope as a fraction. So I'll rewrite -1 as -1 over 1. Using this trick, we can flip the fraction, which actually just gives us back 1 over 1, and we change the sign from a minus to a plus. This tells us that the slope of the pink line, which is the tangent at Q, is plus 1 over 1, which simplifies to 1. We're now ready to find the equation of the tangent line at Q. To do this, we'll use the formula y minus y1 is equal to m times x minus x1. Here, m is the slope, and we found that the slope of this line is 1. The x1 and y1 refer to a point on the line, and here we can use the point Q. This has an x-coordinate of minus 1 over root 2 and a y-coordinate of 1 over root 2. Let's go ahead and simplify a bit. Minus 1 over root 2 is the same thing as plus 1 over root 2. The subtraction of 1 over root 2 on the left-hand side can be removed by adding 1 over root 2 to both sides. 1 over root 2 plus 1 over root 2 simplifies to root 2. Now we've got our equation in a nice format. Y is equal to x plus the square root of 2. Remember, we were told that the centre of S was the intersection of the two tangent lines, the tangent at P and the tangent at Q. We've now found the equation of each of these lines. The equation of the tangent at P was x is equal to minus 1, and the equation of the tangent at Q was y is equal to x plus square root of 2. We can solve these simultaneous equations to give us the coordinates of the centre. And as it turns out, these are a very easy pair of simultaneous equations to solve. That's because the first equation gives us the x value directly. It literally says that x is equal to minus 1. To find the y value, all we have to do is sub in x equals minus 1 into our second equation. When we do this, we see that y is equal to minus 1 plus the square root of 2. Writing our x and y value together in a pair tells us that the coordinates of the centre are minus 1 plus root 2. We were also asked to find the radius, but thankfully this is quite straightforward. Since we are told that P is a point on our circle, the radius will be equal to the distance from the centre, minus 1 plus root 2, to P, minus 1, 0. Since these 2 points have the same x-coordinate, minus 1, the distance between the points will simply be the difference in the y-coordinate. Well, the y-coordinates are minus 1 plus root 2 and 0, and the difference between these two values is simply minus 1 plus root 2. So that'll be the radius of our circle. In question 10, we're presented with a diagram of a right circular cone. The top portion of this cone has been extracted to form a basin. We are given several measurements here. The radius of the original cone is 15 centimeters. The radius of the base of the basin is 12 centimeters, and the slant height of the basin is 10 centimeters. In the first part of the question, we must show that the length from B to E is 40 centimeters. The key to solving this is observing that we have some similar triangles in our cone. Let's focus on the triangles ABC and DBE. Both of these triangles have a right angle. they also share a common angle at B. And since the angles in a triangle always add up to 180 degrees, we can deduce that the third angle must match also. Since these triangles have the same three angles, we say that they are similar. A useful result about similar triangles is that the ratios of the corresponding sides will always be equal. In this question, we were asked to find the length of BE, and I've labelled that here as x. I've also written in some of the measurements that we were given. DE is 12 centimetres, AC is 15 centimetres, and EC is 10 centimetres. In the triangle DBE, the side opposite the right angle is x. The side opposite the angle at B is 12 centimetres. So the ratio of these two sides is x over 12. Since our triangles are similar, we know that this will be equal to the ratio of the same two sides in the triangle ABC. Well, in that triangle, the side opposite the right angle is x plus 10, and the side opposite the angle at B is 15. So the corresponding ratio is x plus 10 over 15. Now we have an equation which we can solve for x. To begin, we can multiply both sides by 15 times 12. Then we can multiply the brackets on the right. 12 by x is 12x, and 12 by 10 is 120. As the next step, we can group our x terms together by subtracting 12x from both sides. 15x minus 12x simplifies to 3x. And as the final step, we can get rid of the multiplication of 3 by dividing both sides by 3. When we perform the calculation, we see that x is equal to 40 centimetres. In the second part of the question, we must find the total internal surface area of the basin. Well, this area will consist of two components. The flat circle at the base of the basin, which I've coloured in orange, and the curved surface around the interior of the basin, which I've coloured in blue. Finding the orange area won't be too bad. All we have to do is find the area of a circle. However, the blue area is a bit more troublesome. To find this, we should look back at the original cone. If we find the total surface area of this full original cone, and then subtract away the curved surface area of this smaller cone, which I've coloured in red, then that will leave us with the desired blue area. Now that we've outlined our strategy, let's go ahead and actually calculate each of the areas. The first result we need to use is that the curved surface area of a cone is equal to pi RL, where R is the radius and L is the slant height. The original big cone had a radius of 15 centimetres and a slant height of 50 centimetres. Subbing these values in gives us 750 pi. The smaller cone, BDE, which I had coloured in red, has a radius of 12 centimetres and a slant height of 40 centimetres. Subbing these in gives us 480 pi. As I mentioned earlier, the curved surface area of the basin is obtained by subtracting these two figures. When we do this, we end up with 270 pi. To find the flat surface area at the base of the basin, we'll use the result that the area of a circle is equal to pi r squared, where r is the radius. We were told that the radius at the base of the basin was 12 centimetres. If we sub this value in, the area comes out as 144 pi. Now that we know the curved surface area and the flat surface area, we can find the total surface area of the basin by adding these numbers together. When we do this, we end up with 414 pi. We were asked to give our answer correct to 1 decimal place. Converting this to a decimal and rounding to 1 decimal place gives us our final answer of 1300.6 centimetres squared. In part 3, we must draw the diagram of the net of the curved surface of the basin. We must include enough measurements so that no further calculations are required to draw the diagram with a ruler, compass and protractor. The following fact is useful when tackling this question. The net of the curved surface area of a cone forms a sector of a circle. Let's go ahead and illustrate this idea on the cone we were given. Imagine that we grab a pair of scissors and cut a straight line from C to B. Then, if we unfurl the cone and push it down onto a straight surface, we'd get a picture like this on the right. The line, which we cut with our scissors, will appear on the boundaries on either side. The base of the basin, which I've drawn in as this pink circle, will correspond to an arc. The top of the basin, which I've drawn as a blue circle, would also correspond to an arc. The curved surface area of the basin will be the region between these two arcs. I've coloured that in grey here. Now that we've got the sketch of our net diagram, we need to make sure we label it with enough measurements so that it could be accurately drawn. From the previous parts of the question, we already know the side lengths. BE measures 40 centimetres and EC measures 10 centimetres. Adding these together tells us that BC is 50 centimetres. These side lengths are useful, but they don't paint the full picture. To be able to draw the diagram, we would also need to know the angle at the base of this sector. I've labelled that in as theta. To finish off this question, we'll need to figure out what this angle is. A useful fact here is that the curved surface area of the cone will be equal to the area of the sector in the net. I should emphasise that we're looking at the full cone here, not just the grey region for the basin. Well, in the last part of the question, we found the curved surface area of the original cone. It was 750 pi. If we equate this to the area of the sector in our net, this will allow us to solve for theta. If you consider the full 360 degrees of a circle, the area of the circle is pi r squared. If you don't have the full circle, but instead have theta out of the 360 degrees, well then you'll have theta over 360 of the area. So the formula for the area of our sector will be theta over 360 times pi r squared. The sector that we drew had a radius of 50 centimetres. We can sub this value in for r, and then simplify to obtain an answer of 2500 over 360 times theta times pi. Since the area of the sector must be equal to the curved surface area of the original cone, we can equate this value to our 750 pi and then solve for theta. Since both sides of our equation are being multiplied by pi, a good first step is to divide both sides by pi and cancel these out. Focusing on the theta, it's being multiplied by a constant, 2,500 over 360. To get rid of this multiplication, we should divide both sides by this number. Performing the calculation on the left brings us to our answer here. Theta is 108 degrees. In part B, Seamus is picking a new 4-digit PIN code. We're told that each of the digits must be between 1 and 9 and that no digit can be used more than once. In the first part, we must work out how many such codes are possible. It's useful here to consider choosing the code 1 digit at a time. We can visualize this by drawing out 4 empty boxes and then thinking about how many valid ways there are to fill in a digit to each of the boxes. Focusing on the first box, we have 9 choices for what we could write in, namely the digits from 1 to 9. When we consider filling in the second box, we're going to have 8 choices. This is due to the fact that no digit can be used more than once. Whatever number we put in the first box will be blacklisted and no longer available for use in the second box. By the time we move to the third box, we've already used 2 of our 9 digits, 1 for the first box and 1 for the second box. This means that there'll be 7 choices remaining for the third box. In a similar fashion, when we reach the fourth box, we've already used 3 of the 9 digits. This means that there'll be 6 choices left over when we're filling in this final box. To get the total number of choices here, all we have to do is multiply together the number of choices for each individual box. This gives us 9 times 8 times 7 times 6, which comes out as 3024. In part 2, we must work out how many of these codes contain the digit 2. A nice way to approach this is to try and find the number of codes without the digit 2. This can be done in the exact same way we worked out part I. We'll lay out 4 boxes for our code and think about the number of valid choices for each box. Since we don't want to allow the digit 2, we're going to have 8 choices of digit for the first box. 1, 3, 4, 5, 6, 7, 8 and 9. Similar to part I, each successive box will have 1 fewer choice than the previous box. This is due to the fact that we're not allowed repeated digits. So each time we write a digit in the box, it rules that out as a choice for future boxes. So the total choices for the number of codes without the digit 2 will be 8 by 7 by 6 by 5, which is 1680. In part 1, we saw that there was 3024 total codes. We found that 1680 of these do not contain the digit 2, so the remaining 1344 do contain the digit 2. In the final part of the question, we need to figure out how many of the codes have the sum of the first 3 digits equal to their 4th digit. The first thing to observe is that most of the time, when you add together 3 digits, you end up with a 2-digit answer. For example, if you added 4 plus 6 plus 7, you would get 17, which is a 2-digit number. If we want the first 3 digits to sum to the 4th digit, this implies that the sum must be a 1-digit answer. And there's not too many ways this can happen. We're also working with the restriction that we're not allowed to repeat digits, and that just restricts the possibilities further. In fact, there's only 7 valid ways you can add together 3 distinct digits and end up with a 1-digit answer. I've listed these here. 1 plus 2 plus 3 is 6. 1 plus 2 plus 4 is 7. 1 plus 2 plus 5 is 8. 1 plus 3 plus 4 is 8. 1 plus 2 plus 6 is 9. 1 plus 3 plus 5 is 9. And 2 plus 3 plus 4 is 9. We have to be careful here. Our final answer won't be 7, and that's because we have to consider the ordering of the first 3 digits. As an example, consider the sum 2 plus 3 plus 4 is 9. We have to think about how many different ways we can arrange the 2, the 3 and the 4. If I start with the 2, there's 2 options to finish off, 3, 4 or 4, 3. If I start with the 3, there's also 2 options to finish off, 2, 4 and 4, 2. In a similar way, if I start with the 4, we again have 2 options to finish off, 2, 3 or 3, 2. In total, we have 6 distinct codes being generated from our sum. So, putting everything together, we have 7 different sums, and each one generates us 6 distinct codes. The total number of codes will simply be 7 times 6, which is 42.